Right, the last thing we'd like to talk about when we talk about orbital motion is artificial satellites. So we looked at natural satellites. Now we want to look at ones that are actually crafted by people. And artificial satellites have been so, like, they've just profoundly changed society in the last, well, basically since Sputnik 1 was launched in 1957. And we might not think a lot about them, but we certainly use them every day. Like, we use satellites for communication, GPS. Like, satellites have been quite revolutionary. Now, with satellites, there's a lot of them in space. The one special type that we're going to actually just look at for a calculation purpose is we're going to look at something called a geostationary satellite. So geostationary satellite's a little special. Like, if you're on Earth and you manage to look up at a satellite, what you'd notice is that when you're rotating and the satellite's rotating, you always end up seeing the satellite. It looks like it's not actually moving. It looks like it's stationary. So both of you are moving together in your orbits. So what we know is that if it takes you 24 hours to make a complete orbit, what we're going to assume is that for a geostationary satellite, it's also going to take 24 hours to make its orbit. So geostationary satellites are special in that they have a period of 24 hours. Geostationary orbits are very popular with communication satellites, but they're starting to get filled up with satellites that are no longer in use. You know, the whole space junk problem. So let's look at the question on this. So we'd like to determine the height above Earth's surface, so altitude, of a geostationary satellite. We'll give the answer to 3 significant digits. Right, so once again, here's Earth. Here's our satellite up here. We're going to find that radius. We'd like the altitude. So we're going to have to subtract off Earth's radius at the end here. Now, let's use little m for the satellite. And let's use big M for Earth. So for all of these orbital motion problems, our starting point is still going to be Fc equals Fg. So I'm going to have mv squared over r. This is going to be g mass divided by r squared. Now, let me correct myself here. For centripetal force, since I know for a geostationary satellite, I know the period is 24 hours, I want to have something with period instead. So we're going to use 4 pi squared rm over t squared, and we're going to have that equal gmm over r squared. So again, the mass of the satellite is irrelevant, and then like the other problems, we're going to cross multiply both sides. So I'm going to get 4 pi squared r times r squared is going to give me r cubed, and I get gm multiplied by t squared. So first off, I'd like to solve for the radius. Let's divide both sides by 4 pi squared. So I get r cubed is equal to gmt squared over 4 pi squared. So to get r, we will need to take the cube root of both sides. So r is going to be the cubic root of gmt squared divided by 4 pi squared. So there's a lot going on here. We have to be really careful. Now, just as a side note, we know that the period for a geostationary satellite, we know that it's 24 hours. So if we convert that into seconds, we know that there's 60 seconds in an hour and 60 seconds, we know that there are 3,600 seconds in an hour. So we multiply this by 3,600. We're going to get that in 24 hours, 86,400 seconds have passed. So we know the universal gravitational constant, the mass of the Earth is in the data book, or on the data sheet. We know the period. Let's find this orbital radius. So we're going to use our gravitational constant times the mass of the Earth times our period for a geostationary satellite. Then we're going to divide all that by 4 pi squared. Again, a lot to put in the calculator. Take it real slow, take it very methodically here. So let's see what we get here. So much to punch in here. So I'm going to get, this is about 4.223 times 10 to the 7 meters. But I need you to remember, that distance is from the center of the Earth to the center of the satellite. We would just like the distance from the surface of Earth. So from this to get the altitude, we have to subtract off Earth's radius, which again we know is that 6.37 times 10 to the 6 meters. So that should be a 3. So what I'm going to end up getting here is I'm going to get about 3.59. What do I get here? 3.59 times 10 to the 7 meters. So what that's telling us is that for a geostationary satellite, its height above Earth's surface is going to be about 3.59 times 10 to the 7 meters. Or it's just going to be under 36,000 kilometers above the Earth's surface. So the key to do this problem is we have to know a geostationary satellite's period is 24 hours.